Hello everyone, my name is Hong Seok from Professor Tai's research group in UC San Diego. In this presentation, I will talk about scalable tactile sensor arrays on flexible substrates with high spatial temporal resolution, enabling sleep and grip for close robotics. As all of you would be familiar with, flexible force sensor array can be used in a variety of future applications, including industrial robots, surgical robots, or neuroprosthetics. In such applications, spatial and temporal resolution of the sensor array is critical to achieve sophisticated movements. The table shows the sensitivity, spatial, and temporal resolution of the human hand. Thanks to its superior sensitivity and spatial temporal resolution, human hand can freely interact with arbitrary objects even without watching them. To achieve such a high spatial temporal resolution, as well as excellent sensitivity, we suggest a transistor which can sense external forces. By combining the functions of force sensing and signal multiplexing into a single element, we can circumvent the trade-off between integration density and sensor performance. Zinc oxide thin film transistor can do this job thanks to its semiconducting and piezoelectric properties. The left figure schematically shows the operation of the zinc oxide thin film transistor that we developed. The dual gate structure provides excellent electrostatic control over the channel, and the piezoelectricity inside the zinc oxide allows the TFT to modulate the current when external force is applied. The transfer curves and output curves are shown in the right side of the slide, showing excellent on-off ratio and good ohmic interface. On the other hand, the on current of the TFT quickly responds to the external force as shown in the right side of the slide. The response is proportional to the amount of force, which makes the TFT to be a good force sensor. Given the dual functionality of the zinc oxide TFT, we developed an active matrix zinc oxide TFT array which will provide spatially resolved force information. The active matrix structure is superior than passive matrix structure in terms of signal contrast and response speed. The left figure shows the as-fabricated TFT array composed of crossing source and gate electrodes. The inset shows the individual TFT in detail. The electrical connection of the active matrix can be found in the right side of the figure. To achieve best sensitivity and temporal resolution out of the TFT array, we designed the custom control hardware. This board consists of 16 parallel two-stage transimpedance amplifiers located at the bottom, which promptly amplifies the current of each row. The gate controller located at the top switches columns of the array. The signal multiplexer, gain filter selection stage, and 16-bit ADC converts the analog signal to digital signal. The microcontroller at the right side controls the chips on the board and transfers data to the controller PC. Let's first take a look about the response of the TFT array to normal force. We applied the same 50 mN force to every single TFT and recorded the response. The heat map plot on the left side shows the response of every TFT in the 8x16 matrix, showing uniform sensitivity over the entire array, except one faulty column at the right. The crosstalk matrix on the right shows the correlation between the TFTs of interest and other TFTs, showing low crosstalk between neighboring TFTs. The response curve shown on the right shows the average current change measured over 0 to 150 mN of applied force, showing linear response over the wide range. The sensitivity was 0.0635% per millinewton with a linearity error of 4.35%. We also performed a two-point discrimination test to show the spatial resolution of the TFT array. The distance between each TFT was 2 mm. As the Nyquist theorem suggests, the array was able to resolve the objects distanced by 5 mm, which is larger than twice of the inter-TFT distance. The discrimination test of 5 mm is similar level to the human hand. We also investigated the temporal resolution of the TFT array. While many researchers claim millisecond response time, they were often limited to the single sensor. We measured the response time of the entire array by doing trial average of the response over moving objects along 2.5 Hz square wave trajectory as shown in the top left. The object applied force on the top left corner of the array as shown in the lower left of the slide. The plots on the right shows the position of the force applicator by blue curves and the average current change of the TFT array marked by the red box by black squares. The response exactly follows the position of the force applicator with response time of less than 10 milliseconds. In other words, the entire array can respond to the arbitrary force in sub 10 milliseconds. Moving on to the shear force sensing, we developed a 3D pillar array to achieve shear sensation. The pillar array covers the TFT array as shown in the leftmost figure. Each pillar covers 4 TFTs and the pillar transforms the shear force into normal forces as shown in the schematics. The rightmost figure shows how to calculate the shear force on each shear force sensing unit based on the response of each TFT in the unit. We experimentally investigated the shear force sensitivity using L-shaped probe to apply shear force to the single pillar as shown in the photo. The response curve on the right shows the response as a function of shear force, showing the linear manner of the response. We measured the shear force sensitivity of individual pillars and plotted the response. We applied upward and rightward shear forces. The response was uniform over the entire array to upward forces as shown in this slide and to the rightward forces as shown in this slide. Given excellent normal and shear force sensation, we demonstrated its application to tactile interface. This video shows how TFT array resolved a single or multi-touch. The position of fingers on the array, shown on the left side of the slide, are well resolved as shown in the response heat maps on the right. The direction and location of the shear force was also well resolved. The quiver plots on the right side clearly shows the location and moving direction of the finger based on its excellent shear sensation. The most important application of the force sensor array is to construct closed-loop control system with robotics. We demonstrated this by attaching the TFT array to each finger of the robotic gripper and programming the control system where the gripper moves based on the input of the TFT array. The diagram on the left side shows the flow of the control program which we programmed. This video shows how the gripper holds the raw egg. The gripper was able to hold the raw egg and kept a certain holding force, which is enough to hold the egg but not as much as to crush the egg. You can see that the gripper holds the egg safely after removing the support. To utilize the shear force sensation, we also demonstrated a slip detection and slip adjusted grip algorithm. When the gripper is holding a heavy object, it slips and increases the shear force at the interface. By monitoring the change of the shear force, the program puts more weight on the gripper and holds the object with higher force to avoid further slip. We demonstrated this by performing the grip experiment with and without shear force feedback. Without shear force feedback, the baseball kept slipping and the gripper was not able to grip the ball. You can see that the baseball keeps sliding at the interface. On the other hand, with shear force feedback, there was no slip resulting in secure grip. You can see that gripper securely holds the baseball and the force slightly increased. The plots on the right side shows the changes of the normal and shear force as well as the gripper angle and threshold holding force computed by the algorithm. Another important advantage of this technology is its scalability. Since our technology is fully based on scalable standard vacuum techniques, we were able to further downscale the devices using the same fabrication process. The photo on the left side shows the miniaturized TFT arrays. The device can be minimized as small as 1.6 by 1.6 square millimeters with pitch of 100 micrometers. The microscope image on the right shows the smallest array that we fabricated. The smallest array provided ultra-high spatial resolution. This array was able to pass the two-point discrimination test at a distance of 750 micrometers and even 500 micrometers, meaning sub-millimeter spatial resolution. This video shows the real-time operation of our smallest TFT array. There is a 1 penny coin filmed together at the right as a size comparison. The high spatial resolution was demonstrated again by imaging the human hair. In this experiment, we placed a single human hair on the TFT array, sandwiched them with glass slides, and squeezed them together. The response map showed a linear pattern at the exact location and orientation of the human hair. In terms of shear sensing, we used the same approach using the miniaturized 3D PDMS pillar array. This small PDMS structure was prepared using a laser engraved mold. The 3D PDMS pillar arrays were prepared on 250 micrometer pitch and 500 pitch devices. This video shows the smallest shear force sensor array where TFT had pitches of 250 micrometers. You can see that the location and direction of the movement of the wooden stick on the array is well resolved as shown in the right side of the video. This video shows the shear sensation more in detail. The transparent plastic rod is sliding over the array. The pillar arrays are being squeezed during the interaction, and the shear force response plot on the right successfully captures the movement. Since the devices were fabricated on the poly-in substrates, they were easily released from the host substrate. We investigated the effect of bending to the TFT performance. The plots on the left shows the change of transfer curves before bending and under different bending radius. The higher bending reduced the maximum current by 2 to 3%, but the overall trend remained unchanged. On the other hand, the higher bending affected the sensitivity. The plots on the right shows the response to the 25 millinewton force as a function of bending radius. The smaller bending radius resulted in higher current change under same force, meaning the sensitivity can be increased by bending the device. We also demonstrated the reliable operation of the TFT array under highly bent condition. We rolled the TFT over the plastic rod with a bending radius 5 mm as shown in the left photo. Both normal and shear force sensation was well demonstrated as shown in the plots on the right side. We also performed bending cycle tests to test the durability of the device. To perform thousands of bending, we used the linear actuator to automate this process. The bending radius was changed from 7 to 2 mm at every bending cycle. The photo on the right shows the TFT arrays before bending cycles and after 10,000 bending cycles. Some crease were observed on the encapsulating polymer layers. However, the devices were fully operational after 10,000 bending cycles. We tested the force response before and after 10,000 cycles, and there was no meaningful changes at all. The response over different forces were measured after 1,000, 2,000, 5,000, and 10,000 cycles and remained similar, indicating that the TFT array can reliably operate with multiple bending cycles. This video shows the application of the sensor array for blood pulse sensation. The array was attached on the wrist where radial artery is located. The temporal response of the TFT array with the strongest response is plotted on the lower left, which shows the typical pattern of the blood pressure. The average response on the lower right clearly shows the different features of pulse signals such as systolic pressure P1, late systolic pressure P2, and early diastolic pressure P3. Another application is waterproof operation and flow detection. Here we encapsulated the TFT array with additional 2 micrometers of pyrrolene C, then tested the array being submerged in the saline solution. The pipette applied the water flow to the array without physical contact. The response evolution shown in the middle of the slide clearly shows that the pressure is locally developed on the upper right region of the array for a small amount of time window less than 100 milliseconds. The shear force distribution on the right side shows that the direction of the flow will be toward upper right direction. This video shows the slow motion video of the water flow detection. And this video shows the waterproof operation of the sensor array being submerged in the saline solution. In conclusion, the zinc oxide TFT performed both force sensing and signal multiplexing, which allowed integration of active matrix array. The device can record normal and shear force information simultaneously. Integration with robotic gripper allowed closed-loop control system, which can grip an arbitrary object and detect shear, and adjusting grip force based on slit detection. Further downscaling achieved best spatial and temporal resolution. The device was fully operational after multiple bending cycles and under curved environments. Demonstrations on pulse sensing or water flow detection promised further application in biomedical devices where high sensitivity and reliable operation in the biofluidic environments are required. I'd like to appreciate the research advisor, Professor Shadi Daye, and we appreciate the support from NSF, NIH, UCSD, the 903 Cleanroom Facility, and Seoul National University. Thank you.